In this video, we'll bring you the kinematic equations of position and velocity functions from integral calculus. Our aim in this video is to see how we can obtain position from velocity and then obtain velocity from acceleration. You would recall in previous videos, by differential calculus, we were able to obtain velocity from position or displacement, is that not so? And we obtained acceleration from velocity. So this time around, we want to reverse the process altogether by integrating. Remember that integration is the reverse of what? Differentiation. So when we integrate velocity, we can actually get position or displacement. And if we integrate acceleration, we can actually get what? Velocity. That's just the concept here. Is that okay? Now to start with, this is a differential equation which we already encountered, that velocity is equal to dx over what? dt. Now if you cross multiply this, we're going to get that dx is equal to v dt. Of course, you know this t in bracket simply means it's a function of time, alright? You might choose not to even put it, it doesn't change anything. Alright, now we have dx equal to v dt. In mathematics, whenever we have a differential coefficient multiplying something, to get the value of that something, you do integration. Look at it. Imagine you have y times dy. To get the value of this term, you are going to integrate this y with respect to y. Is that okay? This dy is a director telling us what the alphabet, the variable you should integrate. If I have something like x dx, it means I should integrate x with respect to x. If I have v dt, it means I am going to integrate v with respect to what? T. And of course, that is not practically possible because v is not the variable t. So if you're asked to integrate v with respect to t, where you have v dt, then that v must have been given as a function of t, so that you now do the integration of that t there. Is that okay? Alright, let's proceed and see how we work on this. This is v dt now, so introducing integral signs. If we integrate this equation, we are going to get this. Is that okay? It's all about integral of this part, dx here is going to produce what? X. Take note, it is not this dx that you integrated. Take note, if you have integral of something like dx this way, this simply means integral x raised to the power 0 dx. There is an invisible x raised to the power 0 multiplying this. That x raised to the power 0 is 1. 1 times the x still gives you what? Dx. So it is this x raised to the power 0 you're going to integrate by adding 1 to it and dividing by the new power. Of course, you do that for polynomial function. If I add 1 to the power of this x here and divide by that new power, I'm going to get something like this. And so the integral dx, of course, will yield x for us. Is that not so? So that's the essence of this. Now if you have integral dx, it's going to produce x. And that will now be equal to integral of this v with respect to t. I'm going to leave this like this, because of course you're not solving the problem yet where v is given as a function of t. When real problem comes, you will see velocity given as a function of time in that case. Once you are done integrating, for infinite integral, you put plus c. So I'm going to use plus c1 here. This c is called constant of integration. So this is actually our position function, which has been obtained from integrating our velocity function. The same thing goes for velocity. To obtain velocity from acceleration, we know this differential equation. So if we cross multiply, we have this, then integrate both sides. Integral of this part, that's integral of this vt, that is a dv. Is that okay? Integral of this dv is going to produce what? V. It also goes with this explanation I gave you. It's going to be integral v raised to the power 0 dv. Is that okay? So it will produce v. Then you have integral of the acceleration with respect to time. And of course, like I explained, you can't integrate acceleration directly with respect to t, except that acceleration is given as a function of time. So in the practical problem, right, in practice, this acceleration will be given as a function of time, just like you saw position given as a function of time in all the previous questions we saw. After integrating, once again, you introduce the constant of what? Integration. I've chosen to use C2 there. Please take note, the C is there a constant of integration, but this C1 has a dimension the same as the dimension of position. What's the dimension of position? L, is that so? So the dimension of C is also L. It means that this C1 here has the same unit as position in meter, SI unit. Then C2 has the same unit as velocity. Because if a problem is given and you solve these, this C2 will have the same unit as velocity. Well, in the next video, we're going to pick a question to see how we apply this integral calculus to kinematics. In this video, we've got this question we want to look at. Okay, let's see what it is all about. A boat traveling at constant velocity of 5 meters per second starts to decelerate to arrive at the dock. Its acceleration is a of t, that is acceleration as a function of time, equals minus 1 over 4t meters per square second. We are required to find the velocity function, the time during which velocity is 0, and of course the position function, given that at t0, x of t is equal to 2 meters. Let's solve this and see. From the question, the acceleration function was given to us. So I'm going to write that the acceleration function is equal to minus 1 over 4 t, then meter per square second. The first part of the question, we have to find the velocity function we do not know. But we recall that the velocity function is given as the integral of the acceleration function. Remember that, right? So we're going to integrate the acceleration function and then with respect to t. Once we integrate this, any result we get, we're going to add a constant of integration to that. So that's going to give us v of t equal to integral. The acceleration function is minus 1 over 4t. Alright, so we're integrating it with respect to t. Now, this is the same as an integration. Constants are usually brought out of the integration sign. So this minus 1 over 4 will come out as constant. We're going to have integral t dt. So the velocity function is now equal to, let's integrate this t with respect to t now. This is t raised to power 1, you know that. So that t raised to power 1 to integrate, simply add 1 to it. It's a polynomial function. So add 1 to this power of t, which is already 1, and then divide by the new power. If you do that, t raised to power 1 plus 1 divided by 1 plus 1 will give you t raised to power 2 over 2. So this will now be equal to minus 1 over 4, open brackets, the integral is t squared over 2. Then we can now add the constant of integration c. Let's see what this is going to give to us. The velocity function is now going to be minus t squared all over 8 plus c. But now, we've not obtained the velocity function completely. Remember, this 8 is obtained from 2 times 4. Then minus 1 times t squared will give us minus t squared. To obtain the complete function of the velocity, we need to know the value of c. So how do we get the value of c? We'll go back to the question, the condition given to us, but v of t is equal to 5 meters per second. The velocity was given to us, of course, at the initial time, t0, when the time is initial. Because what we have here, we are told that the boat is traveling at a constant velocity of 5 meters per second. So that velocity corresponds to the initial time, since it is a constant value. Is that okay? So, substituting that at the initial time, velocity is 5 meters per second. That is now going to give us, in place of this velocity, we put 5 equal to minus t squared. Of course, t is equal to 0 there, so let me indicate at t naught, which is equal to 0. So we're going to put 0 squared divided by 8 plus c. Working this out, the value of the constant of integration is 5. 0 squared is 0 divided by 8 is 0. So this is 0 plus c equal to 5 and c is equal to 5. Therefore, the velocity function is now given as v of t equal to, we go back to this function we obtained, then substitute for this constant, because this constant is a number, and we've obtained the value to be 5. So the velocity function becomes minus t squared all over 8, which is the same as minus 1 over 8t squared, plus c, and c is equal to what? 5. This is the velocity function, and the unit will be meter per second. Now we want to determine the time during which the velocity is 0. You would remember that before the short break we obtained the velocity function for these boats. And we already know that the velocity function, so the second part of the question, recall, velocity function v of t, we got it to be equal to minus 1 over 8 t raised to power 2 plus 5. This was the velocity function, right? So we can now say that at v of t equal to 0, because we're asked to find the time during which the velocity is 0. it implies that the velocity function will now get 0 equal to minus 1 over 8 t squared plus 5. So solving this further would get t squared all over 8. You know, this minus 1 over 8 t squared is the same as t squared over 8 minus. If it crosses to this left hand side, it becomes plus, and that will be equal to 5. Of course, this implies that t squared will give us 40. You cross multiply, is that okay? You cross multiply. Then the value of t will give us square root of 40, which will give us about 6 point something, about 6.3 or so. Let's find out. Square root of 40, 6.32. So 6.32 seconds. So this is the time during which the velocity is equal to what? 0. I want to look at the third part of this question, where we have to determine the position function given that at the initial time t0, x of t will be equal to 2 meters. How do we solve this problem? Remember, we already obtained the velocity function, and you know that position or displacement can be obtained from the integral of velocity. So that's what we're going to do. Let's go to our velocity function. So I'm going to write recall that the velocity function is equal to the value is minus 1 over 8 minus 1 over 8 t squared plus 5. This is what we obtained for the velocity function. So we can now say that we do not know the position function. We don't know the position function, that's what I want to obtain. Is that okay? So, but we know that the position function is equivalent to integral of the velocity function with respect to time. So we're going to integrate this and then introduce what? A constant c. That's going to give us the position function to be equal to integral. The velocity function is given as 1 all over 8, negative of 8 t squared plus 5. So it's going to be minus 1 over 8 t squared plus 5. I'm going to integrate all these with respect to t. Now there's something you should know about integration. It distributes over subtraction and addition. Which means to integrate this, actually it's meant to be equal to integral minus 1 over 8 t squared dt, then plus integral 5 dt. Does that make sense? Although this wasn't necessary, I could have just gone straight and do integral of this, integral of this. Is that okay? But I chose to express it out for you so you can see the real implication of integration over addition, and of course subtraction as well too. The position function is now equal to this minus 1 over 8 will come out of the integral sign as usual, so you have minus 1 over 8 integral t squared. And of course if we do that, we're going to get minus 1 over 8 integral of t squared will give us t raised to power 3 divided by 3. Because we're going to add 1 to it and divide by the new power. Is that okay? So you add 1 to this power 2, you get 3 divided by 3. Then plus, this is integral 5 dt. Remember, you have to bring out the 5, which is constant. You're going to get 5 integral dt. An integral dt will welcome back the variable t. I showed you that when I did integral of dx. I told you the real meaning of that is integral x raised to power 0 dx. So if I have 5 integral dt is the same as 5 integral t raised to power 0 dt. Then you integrate that t raised to power 0. If you do that, it will welcome back the variable t. And this will give us 5t. I am done integrating, so I will put plus what? Plus c. Now we've got a problem here. We don't know the constant of integration here, c. So we're going for it now. I would write at t0, that simply means at time equal to 0. Are you following, right? The position function x of t was given to be equal to 2 meters. Is there? Look at it. So we're going to substitute it into this and then get that this will become x of t, which is 2 meters, equal to minus 1 over 8, open bracket. T is 0, the initial time, so it will be 0 raised to power 3 divided by 3. That's going to be plus 5 times 0, then plus c. Looking at this term will give us 0. Minus 1 over 8, open bracket, 0 cubed divided by 3 will give us 0. So I'm going to cancel it out. This will also give us 0. Let's write that. These two give us 0. So you see clearly that c is equal to 2. Of course, the unit is going to give us a meter as well too. In conclusion, the position function x of t, let me use blue marker to write that. the position function x of t will now be equal to, we'll go back to the integration value we obtained. That's going to be minus 1 all over, this is 3. 3 times 8 will give us 24. So minus 1 over 24t cube plus 5t plus our c is 2. So I'm going to fix up 2 there. And this becomes the position what? Function. If you reverse the process by differentiating this position function, it's going to give you this velocity. And you differentiate this velocity, it's going to give you this acceleration back. So you say now that integration and differentiation, they are actually reverse process. In the next video, we're going to introduce motion with constant acceleration, which of course will move us into motion under free fall, under gravity.